Okay, so yeah, it's recording and the screen is shared, right? Okay. So hello everyone again. So like where we stopped last time, I just wanted to add another point in response to Siddharth's question. So we were looking at these convex sets and convex functions and some things about the convex hull and so on. And then we also talked of the Carathéory's theorem. Okay, so where you say that every point in the convex hull, you can write it as a convex combination of at max n plus 1 points. Okay, and plus 1 points in the original set. So probably as one thing that I wanted to add in this proof, right? So this kind of prompted by Siddharth's question when he asked, like, why can't we go like below n plus 1? Okay, so yeah, of course, like I mentioned something to this effect last time that the expressive power is limited if you go like less than n plus 1. Okay, so of course that still remains that you need to try some examples and find a counter example. But in terms of this proof, one thing to see like where it fails if you are trying to look at it from the angle of this proof. So we looked at this system, right? So we said that you take any x in this convex hull, you can write it as a convex combination of some m points, and we were trying to sort of find some betas here such that these set of expressions are true. I mean, these equations are satisfied. So here, this was a system of n plus 1 with n plus 1 rows and m columns. Okay, so the key thing that we made use of here is that m is greater than n plus 1. Okay, so that's why the null space is non-empty. Okay, so there's something other than 0. By non-empty, mean like it's a non-trivial null space. So something other than 0, and that's where you rest of the assignment of betas. So now if you go like less than n plus 1, okay, so that means the m would be something less than n plus 1. So in that sense, the proof doesn't, I mean, you cannot, you still, you can't say that the system has something other than zeros as the solution. Okay, so in that case, a null space could be empty. Okay, so it's not a complete proof, but in terms of this proof that we gave, like where it requires the n plus 1 is in this point. Okay, so this is something that I wanted to, I mean, I should have added in last time, but I missed telling you. So I hope, Siddharth, there's some more clarity now on this point.
Yes, ma'am.
Okay. Right. So, okay. So this is just something I wanted to clarify. Okay. So are there any other concerns till this point? Any other questions till last class? Okay, so I see that many of you have almost all of you have submitted the assignment. That's great. So I hope things are going fine. So today what I will do is we will look at another topic. I mean, it's in the umbrella of convexity. It's a very important theorem, basically, the separating hyperplane theorem. So this one is kind of like the foundation for several techniques in optimization. And I mean, you may not realize it, but in some of the proofs, it just implicitly, you kind of use it everywhere. So yeah, please pay attention and stop me whenever something is not clear. Okay. So here, this is again about convex sets. Okay, so suppose you have two convex sets, and these are subsets of Rn, and they don't intersect. Okay, so then you can get a hyperplane which separates the two convex sets. Okay, so that's the statement of this theorem. So guys, just a second, there's been some issue here. Yeah, someone's coming. Okay, fine. Okay, so sorry about that. Let me just come back here. So yeah, so C and D are convex sets that are disjoint. Okay, And so the claim is that there is a hyperplane, something of this sort, which separates the two. By that, what we mean is that if you take every point in C, it lies on one side, and every point in the set D lies on the other side. Okay, so that's what is separating hyperplane, basically. Okay, so by now you know what if we write a hyperplane like this, A transpose X less than or equal to B, it means that A is you can represent this as a normal vector here. Okay, and if you recall, that's how the hyperplane was something which satisfied something of this form, right? A transpose X minus X naught is 0 for some X naught on the hyperplane. And so on the hyperplane, you have A transpose X is equal to A transpose X naught, and that's the vector B. Okay, so this is for all points on the hyperplane. Okay. Okay, so from the figure, this is kind of intuitive, right? Like there's a convex, two convex sets, and there's kind of a plane which divides it into two. Okay, so if the sets are non-convex, then this is something that you cannot guarantee. Okay, for example, if you might have something like, say, something of this form and something like this. So then you can't, so these are non-convex regions. Okay, so here, I mean, it's not necessary that you will find a separating hyperplane. Okay, so let's just see the proof of this. So for this class, what I'm going to do is I'm not going to prove it in complete generality. So there are, the theorem just states that it's two convex sets which are disjoint. Okay, so what we will do is we will take a particular case where the sets are closed and they are bounded. Okay, so the ideas would follow. I mean, even to generalize it, it's the same ideas, but it's a matter of some technicalities. So I will focus on this case where C and D are closed and bounded. So these kind of sets where which are closed and bounded, I mean, not necessarily convex, but if they are closed and bounded, those sets are called compact sets. Okay, so let me just write it here. So the reason I'm mentioning this is, when you go back and read some textbooks, okay, there are many proofs of this theorem. And so you might see this, compact mentioned everywhere. So closed and bounded in Rn, it's also called a compact set. Okay. In Rn, a set that's closed and bounded, it's also called compact. Okay, so this in Rn is very specific thing. Okay, so in other regions, something which is not in the space Rn, I mean, you don't say it's compact. There's a more general definition of compact sets, but in Rn it's called compact if it's closed and bounded. Okay, so we will look at this case where the sets are compact and also they are convex. Okay, so that's precisely the theorem. So to analyze this, what we will do is we'll first look at this problem. Okay, so which is basically the distance between the two sets. Okay, so you can represent them as the minimum distance as this optimization problem, right? So it's the inf of this norm u minus v, where u is in C and v is in D. So 1 point from each of the two sets, and whichever minimizes them, that's the distance between C and D. So in terms of this set that is drawn here, it would be something like this. So these are the 2 points I'm talking of. So this is C and this would be D. Okay, so this has the minimum distance, right? So now the thing is that, this optimization problem. So this is a continuous objective and these sets are closed and bounded. Okay, so now if you recall in the preliminaries, we talked of this theorem of Weierstrass. Okay, so it said that if you have a continuous function that you're trying to optimize over, closed and bounded sets, then, the minimum, the infimum is always attained. Okay, it has a minimum, and similarly, even the supremum is attained. So there is a maximum. Okay, so what it means is that there is a point C and D which indeed attains the minimum distance, Okay, so yeah, if you don't remember this, just go back and refresh on the Weierstrass theorem. So this is what it makes use of. Okay, and because this is a norm that you're trying to minimize, the optimal value is attained and it's positive. Okay, because it's a norm. Norms are always positive. I mean, they're non-negative, but here it's like 2 points, which are, I mean, it's a disjoint set, right? C and D are disjoint, so this is going to be a positive quantity. Okay, so the generalization to other spaces also will, you need to do some manipulation on this point, like about the closed and bounded point. If you're trying to eliminate that assumption, you have to, you have to ultimately resort to the Weierstrass theorem, but you need to, make some manipulations there. So I encourage you to think further on this at a later point, after the class. So let's come back here. So now we were looking at this problem, the the distance between the two sets C and D. So let the C and D achieve the optimum. Okay. So now what I'm going to do is I'm going to construct a hyperplane. Okay. And I'm going to show that that hyperplane is indeed something that separates the two sets. Okay. So the way I do this is, it's a very specific setting here, but it's kind of intuitive in the sense like you take this C and D, these 2 points, right? And you construct A as this vector D minus C. So basically this is the vector A, okay? And the B here is, something like this, D norm of D square minus norm of C square by 2. And the claim is that, D lies on one side. So A transpose X minus B is greater than or equal to, greater than or equal to 0 for everything in D. And A transpose X minus B is going to be less than or equal to 0 for every point in C. Okay. So, so we're going to prove that this is what happens. I mean, we're going to prove this claim basically. Okay. So let's just see something about, what are the points through which it goes through. Okay. So the specific reason for constructing this is, intuitively you have two convex sets, and when you think of a plane separating them, one way to do it is, you take the, the 2 points which achieve the minimum distance, and the hyperplane kind of goes through the middle of them. So this midpoint is what it goes through. Okay, so so then if you substitute this value at the midpoint, you have X is C plus D by 2, because this is the vector C and D, so midpoint is C plus D by 2. And now if you just take this value of A and this value of X, and if you substitute, so it's D minus C transpose D plus C and half of that. So what you're going to get is this term. Okay, so norm of D square minus norm C square by 2, and that's exactly what we take as B. Okay, so is this point clear so far? Is it okay? Are you able to hear me? It's all okay.
Ma'am, can you repeat again the last part you said?
About this point, about the midpoint?
Yes, ma'am, the last explanation, like from midpoint of C and D. And
yeah. So so what I'm saying is, like, you have these convex sets, and when you think of a hyperplane separating them, like intuitively what you have is, I mean, if you have these points given to you, the C and D, okay, so these are the points which are the closest 2 points, right, in C and D. So then when you think of a hyperplane, a natural thing is something which goes through this midpoint of this, this C, this vector going from C to D. Okay, so between these 2 points, so you think of a hyperplane as something which goes through a midpoint. Okay, so in that sense, the X that you take, which is C plus D by 2, that's the midpoint, right, of the, like, C and D are here, and the midpoint of them is just this value of C plus D by 2. Okay, so now you recall that, a hyperplane going through this point will have the form A transpose X is equal to B. Right, and so A, we've already fixed it. So because in hyperplanes you look at this notion of normal. Okay, so something which is normal to all the points here. So that is A. Okay, so A, we take that as B minus C. Okay, now to get this value of B, you know a point X, okay, which lies on the hyperplane, so which is the midpoint C plus D by 2. And now if you take A transpose X, what you're going to get is just this term, D minus C transpose D plus C by 2. Okay, so this, if you simplify, what you're going to get is just norm of D square minus norm of C square by 2. Okay, so for any point on the hyperplane, so this is the value of D. So you took a particular point on the hyperplane, which you like it to be on the hyperplane, and you computed the value of A transpose X. Okay, so that is the value you usually take, right, for a hyperplane. So for every point here, you have that A transpose X will be this value. Okay, does that make sense?
Yes, ma'am, I got it. Yeah.
Okay. All right. So yeah, so this is how, I mean, this is the basis for, fixing these values of A and B. Okay, some intuitions behind why it's fixed in this manner. Okay, so now the point is that, I mean, what we need to show is that for all points in D, in the set D, you have A transpose X for this value of A and B. A transpose X is greater than or equal to B. And also for every point in C, you have the other way. Okay, so we're going to prove that now. Okay, so yeah, so the proof is that we'll just show this part. We'll show that this is true. So the other part, for all the points in C, A transpose X is less than or equal to B. That is a very symmetric argument. Okay, the same way like we would show this. I mean, you can apply it in a similar fashion to this one. Okay, so let's just focus on this part. So take any point in D, the claim is A transpose X is greater than or equal to B. Okay, so suppose this is not true. So that means there is some point D tilde such that A transpose D tilde is strictly less than B. Okay, so yeah, some point you're going to see a contradiction to this. So what this means is, if you just substitute A and B, what you're going to get is D minus C transpose D tilde is strictly less than, this is the value of B, right? So this is A, this is the A we took, and this was the B. So D minus C transpose D tilde is strictly less than this term. Okay, so we will use this fact later. So let us just keep this here for now. Okay. So now on another note, so let's just look at a slightly different point here. We'll come back, we'll use this fact that we have derived. Okay, so if you look at this function, right, g of x is x minus c. So suppose you have a c, you're fixing this value of c, and now you're considering this function x minus c squared, where x is anything in the set D. Okay, and now you're trying to minimize this gx. Okay, so now of course you already know that D is the minimum point. So this minimum of g of x should be attained at the point D, at this point. Okay, because you're trying to solve this problem now. Suppose, okay, you have a c, that was a point that out of the all points in the set capital C, the small c was the one that was closest to a point in D. Okay, so now if you look at this objective where it's an optimization problem over the points in D, yeah, so again this is now D is a convex set, right? This is a convex set, it's closed and it's bounded. Okay, so because it's closed and bounded, and yeah, this objective is a continuous function in X, so the minimum is attained. Okay, and because this is a convex set, a local optima is a global optima, right? So you know that it's going to be attained at the point D. So now, so that means there is no descent direction at that point, okay, because it's an optimum. So what we're going to show is that, this D tilde that you constructed earlier, I mean the point D tilde which doesn't satisfy this, and that can be used to construct a descent direction. So basically this D tilde minus D is going to be a descent direction for this problem, okay, at the point D. Okay, so is the idea clear, like what we are going to do, the sequence of steps? Okay, you're all very, very quiet. So is there something which is, it's clear, Siddharth, is clear? Okay. Is there any question till this point? We can go over it a little slowly. That's fine if you have any doubts. Okay. Bhavna?
Yes, ma'am, it's clear to me.
Okay. Okay, so Devansh, you had a question?
So by mistake.
Okay, sure, no worries. Okay, so let me do this. I will just complete this and then, we can again come back if there's any question. Okay, so the idea is to, yes.
Ma'am, this D tilde minus D is pointing towards D tilde, okay, from D to D tilde. So
yes.
when you're saying it is a descent direction for this thing, so what does it mean graphically?
So, so what we have till now is D, we expect D to be attaining the minimum of this function. Okay, so if you go in the direction D tilde minus D, so if you go away from D towards D tilde, so if it's a descent direction, what it means is that this function, this x minus c norm square, that is going to reduce further if D tilde minus D is a descent direction. Okay, so basically there's a region around this D such that if you go in, if you make some steps in that direction, this function is going to decrease. The function value is going to decrease. Okay, so that's what it means when we say it's a descent direction. Okay, so you will recall that, I mean, we had seen some things about this for the case of unconstrained problems. Okay, so it's just an idea of, the function value is going to decrease along this direction. So that shouldn't happen if D is an optimum point. Okay, so that's where the contradiction will lie here. Okay, Rajneesh, is it?
Yes, ma'am. Clear.
Okay. Okay. So thanks for asking this, Rajneesh. Okay. So now, so remember the conditions for a descent direction, right? So if you have a function g, now when do you say a direction is a descent direction? So there's this condition we derived, right? Does anybody recall the condition? Like we saw this in an unconstrained optimization framework, something about the gradient, right? So we had, so some, let me call it P. P is a descent direction if descent direction for the function G, at the point at some x. Okay, for the function G at a point x. So what this means is that we had this condition, right? Like G, grad of G of x times something. What do you remember what the condition was?
Times
Ma'am, it's dot product with P is less than 0.
Yeah, correct. So this is going to be less than or equal to 0. Okay, so if this is the case, then you have a descent direction. So P is a descent direction. So let's just apply that here. Let's see what this value is going to be. So the g of x we are considering is this function, x minus c square, where c is given. Okay, now the gradient, if you take, it's just, this is exactly x minus c transpose x minus c. So another way to write the norm is this. Now the gradient of this is 2 times x minus c. Okay, so so let's just see what happens. Like substitute this. So the particular point we are looking at, the x that we are looking at is the point D. Okay, so we're interested in looking at g of grad g of D. So that is going to give you 2 times D minus C, and the transpose with D tilde minus D. So this is the direction which we claim as a descent. Okay, so we claim that this is a descent, going to be a descent direction. Okay, so now it's just about some algebraic manipulations. So you just expand this, right? So you're going to get d transpose d tilde minus d transpose d. So this is the norm of d square minus c transpose d tilde plus c transpose d. Okay, so now I'm just grouping the terms which have d tilde. So this is 2 times d minus c. So I'm basically taking these two. So that gives me this term. And now everything else which has d is going to give me this. So again, d minus c transpose d. Okay, so now we will use something which we just showed some time back. Okay, we said that since d tilde is a point which violates this, we have this condition is true. So that's why we again have the same term coming up. So d minus c transpose d tilde. So that comes up c square. Okay, so 2 times this, so norm d square minus norm c square. And then expanding this further, you're going to get minus 2d norm d square plus 2c transpose d. Okay, so now what happens? So you have a 2 and 1 and minus 2, so that kind of cancels. So you have norm c square, norm d square, and 2c transpose d. So this is just the norm of c minus d square. Okay, so negative of that. And so this is going to be less than 0. Okay, for sure, because c is not equal to d. And you have this negative term. And this part alone is always going to be greater than or equal to 0. But in particular, since c is not equal to d, you have that this is positive, and negative of that, it's going to be a negative quantity. So what we have just shown now is d transpose minus d is a descent direction for the function g at the point d. Okay, so the function value decreases and that cannot happen, right? Because d was the point for which this g of x was a minimum. Okay, g of x attains a minimum at the point d. Okay, so any questions here?
Ma'am, how did we write that step that that norm into the square?
Which one? So that which point are you? Is it something in this these part?
Yes, ma'am. Ma'am, where we did that c minus d square, c square minus d square plus 2c transpose d.
Oh, this one?
Yes,
Okay.
ma'am. How did we reduce it to c minus d square?
Oh, this one. Oh, okay, okay. So this one is just the norm of c minus d. So let me just.
Ma'am, but if I write it like this, c minus d transpose times c minus d, then the two terms which I get are d transpose c and c transpose d.
Yeah, but those are two vectors, right? So d transpose c and c transpose d. So both are vectors, so you will get the same value. Right? So let me just write it. So c minus d transpose c minus d. That's what this norm is without the negative sign. So you'll get c transpose c minus c transpose d minus d transpose c plus d transpose d. Right? This is what you get. Okay. So your question is why these two, how is it the same? So if c transpose d, so c and d are vectors in Rn. Okay, so these are 2 points, right? And those are in Rn. So c transpose d is just the summation I equals 1 to n ci di.
Yeah.
Okay. Okay. Similarly, d transpose c is also the same thing. Okay, so that's why these get combined, and you have this. Okay. Sorry, no. Yeah, this one. Okay, yeah. So yeah, thanks Siddharth for asking that. Are there any other questions on these steps? Is there any confusion in the overall flow of the proof? Okay, you're all very quiet today. So let me ask somebody. Ankit? Ankit, are you there? Okay. Ankit has disappeared. Okay, fine. So Ankit is not here. What about Anushri?
Yes, ma'am, it's clear.
It's clear. Okay. Anybody else? Avinash?
Yes, ma'am, it's
Yes,
clear.
clear.
It's clear. Okay. Okay, good. Okay. Okay, Ankit said there's a lot of noise. So is it clear to you, Ankit? Are you able to hear and are you able to follow? You can type. Okay, good. What about, yeah, Devyani? Is it clear? Devyani, Bhavna?
Ma'am, actually, I had a question. What was the intuition behind knowing that such a contradiction is going to arise? Because I understand, I follow it algebraically, but I don't see why, I don't see how such a contradiction would have come. So intuitively.
Yeah. So with respect to intuitions, I mean, okay. I guess your question is something like how can we, if we were to do it on our own,
Right.
how would such a thing strike, right? So yeah. So for many of these things, it's just not very immediate how you could start thinking about this. I mean, this is my take on this. For many of these problems, I think it would have come through some examples. I mean, I think this is something which has taken like it is like one of the foundational results, right, in optimization. So it would have taken people some time. Like it would have they would have really worked on some examples, and gradually they would have got this idea. Okay, so yeah, so it's not like very immediate to me. Like why? I mean, how one would go about starting to think of something like this. Perhaps even because many of the proofs that are there, it just, I mean, that's the thing with all these contradictory proofs by a contradiction, right? So it's just a way of expressing, some result is true. Okay, so yeah, Devyani, I think I don't have a clear-cut answer to your question. Okay, so yeah.
Okay.
Okay, so one thing that would help is, I mean, maybe like, you can also see some of the other proofs. So for example, like Boyd, Boyd's textbook, the proof is slightly of a different nature. So you can also try taking a look at that. So there are some proofs which seem like even more algebraic. So yeah, so I mean, I felt like, I wanted a proof where, the algebraic details are as minimum as possible and with more ideas. I agree, this does not have like the full set of ideas are not very evident. But yeah, that's how many of these things are. So yeah. So yeah, Devyani, sorry, I don't have a full answer to your question. Okay. So are there any other points, anything else you want to clarify about the others? Jaswant? Jaswant Gurti? It's clear. Okay. Okay. So, what I want you to take from here is I just want you to get an idea of this overall proof. Okay, the overall proof idea, like the sequence of steps that we went about showing it. Okay. So yeah. Yeah, Rajneesh.
I think there is a clear intuition behind this. What Devyani asked. Ma'am, what we are doing is we are trying to find a different point D tilde, which is closer to C. Only
Yes.
that way that it would be on the other side of the plane. But due to the convexity of the curve, we are showing that is not possible.
Yeah. Yeah, that's true. That's exactly what we are doing. But why do we think of something of this thing, right? Like about why is this a descent direction? Why did we go along this angle? Like why is it like very immediate from the construction from this geometry as to why if you take this t tilde minus d, is it very obvious that why that becomes a descent? And how do you know that this is the direction you have to take? I mean, how do you know that this is the proof that you should go through? Like to show contradiction, but how do you know that you should go via this idea of descent directions? So I think that that is not. I think that was what Devyani's question was. So if you have some thoughts on it, please do share, because that helps. I mean, we all learn in the process. So Rajneesh, was it clear like what the issue was?
Yes, ma'am.
Yeah, thanks for attempting it, and I encourage you guys to go and think.
It sort of answers my question, what Rajneesh brought up, and it also sort of explains why d tilde d would be a descent direction, because essentially we are just saying that d tilde is going to be closer to c because we are saying it's going to be closer to the plane. So that just tells us that the function would have another lower minima, which was not d, and we essentially choose a descent direction in that direction. So
yeah, so for so instead of choosing D, we would even have chosen D tilde to construct that hyperplane.
Yeah, exactly. That's the idea behind this proof. Yeah, I mean, okay. So probably I might have misunderstood your question. So yeah, okay. So yeah, the sequence of steps is just this, right? Like, so you take the minimum of this function, the minimum distance, and you have some point which takes the minimum distance. And yeah, so maybe another thing is, suppose, so if d tilde didn't satisfy this, maybe it would be somewhere here, right? So that's what we are saying, right? So the separating hyperplane is something here, but the d tilde, I mean, I think this figure was drawn badly, but so d tilde would be something on this side. Okay, so that's what it would be, but then it cannot be part of this set. Okay, so because then there would be something, maybe something closer here. Yeah, that perhaps that's the, yeah, you can think of it in that way. Okay, so yeah. So I hope, yeah, I think these things, this kind of discussion is good. I hope this helped to clarify many other questions, both of you, Rajneesh and Devyani. It's nice that you guys thought of these intuitions. So yeah, so please ask if there's anything else which is bothering you on this. Okay, so if not, we will just look at, okay, so one thing that, where did we use convexity here? So we did all these proofs, and I went through this proof idea and everything, but where did we use convexity exactly? Any thoughts on this? So is it clear to you, like where, like if you look at the sequence of steps, we just constructed some hyperplane, and we said that this is greater than 0 for everything in D, and we went via this method of contradiction where we took a point d tilde which didn't satisfy, and we showed a descent direction. Okay, so basically we said that this is going to be a descent direction. So where does it use convexity here?
Ma'am, I think to minimize the function x minus c square. Because
So
I mean, we said that if we go along the d tilde minus d direction, then we wouldn't find a point which is any better than d.
Okay, so
In
in the sense here,
hyperplane.
pardon?
We used it in constructing the hyperplane and finding the hyperplane.
So for finding the hyperplane, we didn't use it, right? So we just took this as like something in between, which, I mean, we took a point which is the midpoint between C and D, and we looked at this vector D minus C. So here we didn't use convexity, right? So one thing, who said this about minimizing this function?
No, it's me, Nidhish.
Nitish, okay. So yeah, to some extent, yes, we used it here by saying that, you know, we have a global optima for this because D is a convex set. But actually, strictly if you see, like, okay, suppose, you know, for if you have a local optima, right? So even then you should not have a descent direction. So this thing was just an add-on thing that we had, that it's a convex set. So yes, this point is going to be a global optima. But now when you say a descent direction, right, like even if some point is a local optima, there shouldn't be a descent direction. Okay, because you know, in a local neighborhood around it, you shouldn't the function objective should not decrease. Okay, so in that sense, actually this is not very critical, right? Like, because like for a descent direction, if this is a descent direction, then any small step you make in this way also will cause a reduce in the function value, so it will not even be a local optima, right? So yes, we stated that it's convex, so then there's a global optima, but it's not critical at this point, right? So there's some point at which, you know, it was, I mean, did we miss it, or is it not true for convexity, or it doesn't require convexity? What is your take? Anybody else wants to attempt this? I didn't explicitly state it here, so yeah, I mean, if you have any guesses, please feel free to say.
Ma'am, please could you scroll down to the part where we resolve the contradiction?
This one?
Yes, ma'am.
Okay, so let me just tell you, like, if I don't know if anybody else wants to attempt this further.
Ma'am, I think we used it when, so we took that directions C minus T direction, and we thought that a plane perpendicular to this and passing through its middle point will be our plane. This is when we used that. I mean, see, these two sets can have convexity, but we just require that the two closest points. So that convexity shouldn't be such that you know, that the set goes beyond that and then comes again towards the other set, and and it crosses that initial barrier. I'm not sure if I was able to convey what I want to say. But
so
like, ma'am, so the thing is that these sets could be convex. So if yeah, so these sets could be convex. For example, if you have your two palms right facing one another, then your fingers are not really convex, right?
Right.
But as long
Right.
as your middle fingers, I mean, there are no other fingers which protrude farther into the other set than your middle finger, for example, then we are okay with it.
Oh, okay. I think I got what you said. So something like this, right? Like if this d tilde comes here, then maybe it's a symbol of like non-convexity, something of that kind, right? Is that what you're
Yes,
saying?
ma'am. Yes, ma'am. So, ma'am, even these sets are allowed to be non-convex as long as they don't cross the points of minimum distance.
Yeah, I'm not. I mean, that would require a formal proof. If any form of non-convexity, if we are saying that that's allowed, but so yeah, actually, yeah, in this proof we didn't make use of something of that kind to what you're saying. Okay, but maybe that's a way to even look at it. But like where this proof kind of implicitly made use of convexity is this fact that, you know, if you take a descent direction, yeah, you don't want to go outside the set, right? So this d tilde minus d, so it's in some way it is kind of aligned to what your answer was, Siddharth. But to be more specific, it's like, you know, this direction d tilde minus d, if you make a small step along this, you want to remain in the set d. Okay, So that will happen only because of convexity, because d tilde and d are 2 points on D. So let me just write it here itself. Okay, so this is the d tilde. We assume that it's a point in the set D. So any line on this belongs to the set D. So that's why if you make a small progress in this direction, it's a descent direction, but you also, I mean, now it's a constrained optimization problem, right? Because X should be in the set D. So some point you take here has to lie in this set D. Okay, so that's where the convexity plays a role here. So something between D and D tilde that is guaranteed to lie in the set D only if it's convex. So like what Siddharth said, like, yeah, if you take something in this point, if it comes here, like if you come, if it is non-convex, then, it's not guaranteed that you will, have these points belonging to the set D. So something of this sort, and maybe, okay, something here. I don't know how to really draw it, but the closest points are here. And if you draw this hyperplane, maybe something like, okay. So something, in this part, which is, okay, it's a very bad drawing, but anyway, you get the idea, right? Like, when you take a small step away from D towards D tilde, it should remain in the set D. So that is an implicit assumption that is made here. Okay. So yeah, so this also brings me to this notion in constrained optimization of descent directions. So in unconstrained, we only needed this to be less than 0, less than or equal to 0. But in constrained optimization, this direction P that you take should also be feasible. Okay, it should, in the sense that the new point X that you get, the X tilde you get, has to be feasible. Okay, when you move away from X towards the next point in the direction P, the new point has to be also feasible. So that is also a new condition that comes up. Anyway, we'll see this later when we discuss more on constrained optimization. Okay, so now with this, like, I also wanted to talk of this another theorem called the Farkas lemma, but for that there is a variant of the separating hyperplane theorem. Okay, so what we saw so far was two convex sets. Okay, but now if you take one of the sets as a closed convex set, and this closed is really important. Okay, if you take a closed convex set, and now if you take a point, okay, instead of another set, okay, now between these two also you can separate it with a hyperplane, but here the separation is strict. Okay, so in the sense that you can find this hyperplane A, such that if you take all points in Y, you have A transpose Y less than or equal to 0. And then X has to be like A transpose X is strictly greater than 0. So if you remember in this part, when you had two convex sets, the strict separation was not necessary. You had like less than or equal to and greater than or equal to. But when it comes to a point, separating a point and a convex set, which is also closed, the result is that it is strictly separated. Okay. So one thing you should think of is here why this closed is important. Okay, so this is something I leave it to you to ponder about this. Okay, it is a simple thing. You can see it with some examples why closed is necessary. Okay, so this version of the separating hyperplane theorem is something which we will use in the next time when we study Farkas lemma. Okay, so I will stop at this point, and maybe if there are some questions, I will hold on for some time. So yeah, thanks for coming, and yeah, we'll see you tomorrow. So I'm here for any questions. Yes, tell me, Siddharth.
Is there a notion of local convexity? Because I think what Siddharth was saying was that there should be a local convexity. It doesn't need to be the case that the set itself needs to be convex, the whole set. But even if it is like the example which he gave, even if it is convex in the region considered, like in the region which we are like the closest points, if at that local surrounding it is convex, then our objective would be satisfied.
Yeah. So yeah, perhaps a convexity, like demanding a convexity of the full set, it's maybe a very strong condition. But yeah, this is something. Perhaps, I mean, this is not known to the best of my knowledge. Okay, so maybe there's something you can come up with here, but yeah, to characterize this notion, it's not very immediate how you do it. Okay, like yeah, I understand what you're saying. Something to the extent of, you know, like neighborhoods we have. So in the local neighborhood, it's convex. Yeah, this is something that it's not. I mean, I don't know if there's any result along these lines at the moment. Yeah, but yeah, it's an interesting thing to think of, right?
Ma'am, I have a doubt.
Yes,
Ma'am, I
Nitish.
didn't understand why we had like a strict condition for the second case, and for the first case we allowed that A transpose C to be equal to 0 also. Like,
So this one, right? Like why it
yes,
is
yes,
this. So here, this is like, you know, you can get some examples of this case. Okay, so where you know, you cannot get a strict separation here. For example, I think there's some like commonly used examples, okay, that people give. So let me just, so something like this, okay. So you know, you have like in R2, okay. So one set is, you know, all of this region, okay. Okay, and the other one may be something like this, okay. So something along this lines. It comes very close to the y-axis, but it never touches.
And what if we have two circles with a common point in R2?
So two circles with a common point. So remember, these two sets have to be disjoint, right? So that is an important part, that it's disjoint. Okay. So if you take this kind of an example where one side is, you know, like all of the left side of this plane, okay, and the other thing is this set here, everything here, and this is, you know, gradually coming very close to the y-axis but never meets the y-axis. Okay, so so then these two, you cannot have a strict separation, right? So there'll be some point for which, you know, it will be common, you know, or at least it approaches to be common for that. So that's why you cannot strictly separate these two. Okay, so that is one. Yeah, there are some other examples of this that, I mean, these are commonly studied. So Nidish, I hope this is clear.
yes, ma'am.
Yeah. So if there are any other questions, feel free to ask. But if for the rest of you, you can leave